Okay, good thing I didn't say. Actually, what I did say was probably the thing we don't want on YouTube anyway about our faculty search, but good. So what we're trying to do is to create large-scale entangled systems, and entanglement is really sort of the key ingredient here, the enabling piece. And a lot of applications that we're well aware of here. We could take a brief look at how entanglement plays a role. So for example, in metrology and sensing, we're becoming more aware that entanglement can help take us from sort of uncorrelated, just qubits, to performing our sensing, to correlated states that can suppress quantum projection noise and take you below the standard quantum limit in terms of your sensitivity. Okay, in terms of materials, we have a strong condensed matter community here. There's a lot of entanglement intrinsic in certain types of materials. For example, spin liquids are characterized by long-range entanglement, and dynamics often is highly non-trivial because of this. And so being able to sort of simulate this behavior efficiently is extremely useful. And then computation, of course, the goal would be to have a large-scale quantum computer where you can just kind of calculate or simulate really anything in sort of a digital context, kind of in the way that we use our classical computers today. And finally, communication. We want to eventually be able to sort of link these technologies together, distribute this entanglement over long distances. Cryptology is sort of the main, cryptography is kind of the main application people keep in mind, but generally even distributed sensing or some quantum version of the internet is sort of a large-scale goal that a lot of us are sort of driving towards. Okay, so sort of broadly speaking, where are we in this race to build large-scale quantum systems? Well, let's take a look at kind of how we think about quantum systems. We may have some large number of qubits, and we can do, shown here in blue, like single qubit operations. We can do entangling operations involving more than one qubit. And then at the end, perhaps maybe we measure all our qubits. And the size of the system would be characterized by how many qubits you have and how deep you can go. And the battle, of course, the reason we don't have large-scale quantum computers already is we're fighting against decoherence in these systems, and you can only go so deep before your qubits kind of decohere. And to phrase this in another way, there's an environment out here, and we're trying to build larger and larger systems without the environment sort of taking a hold of what we're trying to do. But the environment is always, watching us very, very closely. So we just went through a Monsters, Inc. phase with my daughter in our household. So the environment is watching us very closely, and so the task is to sort of isolate such large quantum systems and sort of package them in a way so we can do the operations we need to do, but the environment can't cause everything to kind of decohere. But of course, eventually you have some couplings to the environment, some holes in your box, and then once the environment can see what you're doing, it can see whether your cat is alive or dead and sort of collapse all the superposition, all the entanglement that you have inside. So broadly speaking, this is sort of the battle against decoherence, against openness, if you like. And so to sort of state it in that way, decoherence you can sort of view as kind of a finite coupling to your environment, some sort of holes in your box that you're kind of thinking about where they are and maybe how to patch them. And measurements from the environment act to sort of kind of reduce the amount of entanglement. And this is sort of a kind of a fundamental picture or sort of a general perspective. And it's actually an extremely active field now, perhaps sounds obvious, but studying this sort of interplay of many-body decoherence, openness in your system versus the growth of entanglement. And so there's this notion of like measurement-induced phase transitions and the study generally associated with that area, which you can do by intentionally putting in measurements at random in your circuit and sort of controlling the probability in each layer of your circuit as time moves on that you have these measurements in there. And it's pretty well known and a little bit to a small extent studied now in experiment that there are phase transitions and sort of a rich phase diagram as you vary the amount of openness and the amount of measurement in your system. So perhaps this is not surprising, but this is really at the heart, I think, of figuring out how many-body decoherence works and what the battleground kind of looks like in this war against decoherence in terms of making larger and larger quantum systems. Openness can also be a tool, extremely useful tool, so you can use it to prepare states. Sort of a canonical textbook example is like teleportation, where if you have some unknown state on one of your qubits, you can entangle that with other qubits, and then you actually perform measurements, do feed forward with some local operations, and teleport your unknown state from one qubit to another. There are like many body versions of this that people are thinking about recently, where perhaps you start with some complicated many-body state. For example, this thermal field double state is kind of like a finite temperature GHZ state. GHZ state you can sort of think of as being infinite temperature. And then if you perform some measurements of one part of your partition and some classical communication, maybe local operations, you can teleport a many-body state by using openness and feed forward. And there are many other examples. In principle, when you have entanglement growth in a system, you can beat so-called kind of speed limits associated with your interaction energy scale by performing measurements and feed forward kind of sort of non-locally. And you can use this to kind of create classes of entangled states, starting from other maybe less entangled or simpler states. Even in creating many-body states, you can have, again, perhaps this like thermal field double state divided between sort of two sectors. And if you can selectively, use one part as a reservoir and then like trace over those degrees of freedom by measurement, you can sort of at will prepare many-body entangled states with finite temperature, which can in principle be harder to calculate or in a much sort of denser or richer part of the many-body spectrum. And then a little bit more practical, you can perform like collective measurements where you have all your spins and you measure them in such a way so you kind of lose the which way information, and that actually projects that system itself into an entangled state that respects that symmetry, often like a spin squeeze state. And even quantum communication, quantum networking, I view in a similar context, where you have perhaps remote qubits that you can entangle with light when you perform that measurement, and then perform like a joint measurement that again erases this which way information and is a special kind of Bell state measurement that projects your qubits themselves into entangled states. So openness is an extremely useful tool in that context. Even more, as we're probably also quite well aware, if you really want to process information, measurement plays a crucial role there. We're all quite familiar with error correction, for example. So this is a picture of a distance 3 surface code where you have your 9 data qubits, you have 4 stabilizer qubits for X and 4 stabilizer qubits for Z. And this was done very recently with superconducting circuits, but you can see as you go, you have to do a lot of measurements on your stabilizers, and you just repeat this over and over. So by the way, this bar with these little dots, this is borrowed from like music theory, music staff kind of conventions. I think that's kind of cool to see that coming into quantum circuits now. But openness is a key thing here where you measure these errors and you can correct them in real time. And taking that perhaps to its logical conclusion, maybe you can do measurement just with errors, or maybe you can compute just with measurement. That's what I meant to say. So you can start with an entangled state, like a resource state, and then you can just do measurements from there. So you would start with a global state, and then as time goes on, a global cluster state, you would just do measurements on all of your qubits. And really what you're doing here is performing measurements in different bases. And this sort of has a mapping onto this kind of typical gate type model. Okay. And for certain hardwares, perhaps it's easier to do a lot of measurements than it is to actually do like single qubit or 2 qubit gates, for example. Okay, so that's a somewhat broad general overview. And the statement is that it's sort of a grand challenge in the community to have highly coherent, large-scale quantum hardware where you can put in this openness, this ability to perform measurements at will in a scalable way. And so far, a lot of people that are really good at doing a lot of these measurements and things like that do it in a way that's in principle not that scalable, or it would be difficult to really scale to large systems. Okay? Yeah.
All of these examples and you're calling that open.
Yes.
Whereas I think often of openness.
Yes, okay, so this is a good question. And so from my perspective, maybe it starts to get a bit hardware specific, which is where we're going to go now. Of course, if you have your system that's in some environment that you don't really control, and you want to study everything that's going on there, that's an important question. And I would say that's a little different than what we are considering here, where everything we want to be extremely controlled and sort of happen at will. However, there's always decoherence, and so you could sort of cast that type of openness into intrinsic decoherence that's kind of there. In our case, in most quantum computing platforms are not strongly coupled to some kind of environment, so that bath is weakly coupled. But of course, there is some coupling, and it's exactly this decoherence and coupling to the bath, which requires us to use error correction sort of to begin with. Okay, does that make sense?
Into non-demolition measurements, or do you do demolition measurements and still get some of these?
Excellent question. So non-demolition measurement, that's, I guess depends exactly what you mean by that, or whether you mean that sort of like in a textbook way, but we'll see this a little bit later. I guess quantum non-demolition measurements, it's still a strong, fully projective measurement, I would say. It just keeps you in your sort of computational basis, which is kind of the textbook measurement, which is kind of assumed. So if you measure you're in 0, then you are in 0. If you measure that you're in 1, then you are in 1. That's kind of assumed, but in most hardware platforms, that's not to be taken for granted, as we'll see a little bit later. Other questions? Okay, good. So now, obviously, it starts to become more hardware specific. And so where I'd like to go from here is to tell you about the Rydberg atom array platform. And the developments have been, quite remarkable over the past years. And this toolbox of measurement, this element is sort of one of the remaining things that we kind of need to really figure out and bring to this platform in a fully controlled way. And our approach to do that, I'll tell you about. We want to use a sort of a richer level structure as kind of the initial platform, and encode our qubits in metastable states, which help us sort of control the amount of openness that we have. And then I'll tell you about what we're doing, and actually we have 2 experiments that go in kind of similar directions, generally speaking. And we have kind of exciting results, I would say, in these sort of directions on the first experiment, and even the second experiment now is making nice progress, which I'll briefly mention. Okay, so let's look at Rydberg atom arrays. What does this mean? What can we do here? Well, neutral atoms are a very nice platform, sort of from a fundamental perspective, just because the atoms are neutral and we can control them in quite large numbers. And so as a community, we've gotten very good at having large systems of neutral atoms with large particle numbers that we can read out each atom individually in variable number of dimensions, including even like 3 dimensions. And so that's nice to have a scalable system where you can really control a large number of your sort of fundamental qubits ultimately. And also, as I mentioned a little bit, they're very weakly coupled to any sort of environment. They're held with lasers, they're not directly in a crystal or touching anything. And so you can get quite long coherence times typically in this system. And sort of the salient features here is that we can have hundreds of atoms that we can control individually in this sort of platform. And the coherence times are very long compared to gate times. And you could sort of quantify this also as just how indistinguishable or how identical all your qubits are. And particularly in the context of optical atomic clocks, now the level of indistinguishability and precision is quite unprecedented. So in principle, this is a great platform, and it's been active for quite a long time. So where are we now, and what's sort of limiting this progress? Yeah. Yeah, so I guess so in analogy to kind of solid state systems, you may have like local strain or some like spectral diffusion or things like this, where your environment is a little bit different in each individual place. In sort of atomic type systems, if you have a magnetic field gradient or some kind of local Stark shift, or your traps are not quite the same, then that can make your qubits effectively look a little bit different. Okay. Good. So since the atoms are neutral, the reason that the neutral atom platform is a little bit behind, I guess you would say, the trapped ion and superconducting circuit platform is because interactions are sort of not like built in, do not sort of come for free. And so there's been, of course, a huge amount of effort to engineer interactions that you would need for generating entanglement. You can either use atoms that are sort of intrinsically magnetic, although this is actually quite weak and hard to use in this context. You could sort of couple them to light, maybe in sort of a hybrid scheme where you have a optical waveguide or an optical cavity, and use light to mediate interactions. This is a bit challenging because single atoms don't couple to light that strongly, it turns out. In principle, you could go beyond just one atom, maybe use a pair of atoms and use electric dipole interactions to mediate entanglement between your qubits. And what I'm going to talk about, what has sort of, I think, really become a very exciting and quickly moving field, is to use atoms in very highly excited states, or maybe your principal quantum number approaches 100 or so, and then the properties become extremely exaggerated. The size of the atom is like almost classical at some point, kind of approaching a millimeter scale, and you can get very, very strong, like induced dipolar interactions. So this idea has been around for a while, but it's becoming very successful recently, which is what I'll tell you about in a minute. So now that we have that, let's think a little bit how this Rydberg blockade can give us entanglement, can give us interaction. So imagine you just have two atoms, imagine they're super far apart, and you drive from a ground state to a Rydberg state. Well, what states are available? You can have both in the ground, one in a Rydberg state and one in a ground, or both in a Rydberg. And if they're really far apart, they're not interacting, those three states are equally spaced. It doesn't matter that there's interaction between Rydberg if your atoms are really far apart. But of course, as you bring them closer together, you get this induced dipolar interaction, which is van der Waals and scales as the sixth order, but it's actually quite strong on a couple micron scale. It's a pretty enormous energy shift. And so what that means, if your atoms, if you're driving the system with some characteristic Rabi frequency, and your atoms are close enough together within some characteristic length scale, it's referred to the blockade radius, then you simply cannot, you're sort of unable to go to this doubly excited state because your Rabi frequency is at this point sort of smaller than the detuning, the energy shift associated with going there. And so within that regime, it's sort of out of your Hilbert space to be doubly excited. And this is a so-called blockade radius. And inside that radius, you can isolate a two-level system where the upper state is an entangled symmetric W state. So this is sort of the working principle for how entanglement works in this type of platform. Okay. Now, the way that the progress has really moved forward quickly in using Rydberg-based entanglement is getting good at controlling individual atoms and sort of moving them around at will. And this is done with what we call optical tweezers, where you can load from a magneto-optical trap into a tightly focused dipole trap, which we call a tweezer because the atom is attracted right to the center. And this has been done for already 20 years. This is not new. But if you want to scale this to a large number of sites, the problem is that you're not loading deterministically. You're loading stochastically, and so you have a large number of holes. And that's what's made this approach not scalable until recently. But recently, the community has become very good at sort of performing measurements to identify which sites have occupation and which do not. and then sort of feed forward or use that information to compactify your array and remove defects. Okay? So we call this sort of rearrangement typically, and this has been done quite successfully now with hundreds of atoms, in fact. But this is sort of a picture of how it looks. Maybe this is what you start with, right? When you load, you see, you know where your traps are, so you know like what regions you're interested in. You see where they're empty and where they're not, and then you can use that information to change where your traps actually are. So this is an example in 1D. The techniques are slightly different in other dimensions. The idea is still the same, though, that you're using measurement here to reduce your configurational entropy of the system. And that's actually very fast and very efficient compared to reducing your entropy by cooling to something like a Bose-Einstein condensate and then loading into a lattice. Yeah. Yeah, excellent question. So there is limited lifetime of Rydberg atoms. There's a lot of other problems with Rydberg states. Actually, they repel. They're repelled by optical tweezers. But this you should think of as like a initialization. You make your array, you initialize whatever you want to do, and then you would excite to Rydberg from there. And in fact, the Rydberg part, the excitation part, is extremely fast. It's way faster than any of these timescales. It's even faster than motion of the atom in a trap. And typically people actually turn their traps completely off. So it's sort of a frozen regime where the Rydberg interaction is done with atoms just kind of hanging out in empty space. Yeah, Paul.
Do you have to worry about when you're doing cooling afterward, or do you not?
Good question. Yeah, heating can happen if you go a little too fast, if you're not careful. Often people cool while they do this type of rearrangement. But I would say people have gotten pretty good at doing this without a lot of heating happening. Good. So people can do this now in 2D and even 3 dimensions. And this is, optics tricks for 3D. 2D is sort of a kind of a natural extension from 1D, although it is more complicated. And these slides are already pretty out of date. Now people have defect-free arrays of hundreds of atoms in 2D. Okay, so with that, what is the state of the art now? What are we doing in this field? So again, returning to the sort of the 4 research areas in quantum information science, something that I was involved a bit too in this work as a postdoc. We can use these atom arrays as sort of a new generation of optical atomic clocks, where now we can have large numbers of atoms, but we can read them out individually. We can control them individually. We can perform correlation measurements across the array. We can identify systematic or local shifts and in principle correct those atom by atom. And what's more is in this platform is very natural for engineering entanglement. So here's a recent demonstration where Rydberg mediated entangling gates are added to an optical atomic clock to again improve precision in principle below the quantum projection noise limit. Quantum simulation is perhaps the most active field because it's analog and relatively simple. And here people have done quite remarkable things with hundreds of atoms. We've heard about topological spin liquids, other dynamics, a lot of quench studies. It's really kind of an exciting and very active field now. Quantum computing has also made a lot of progress recently. I heard recently the gate fidelity is now sort of beyond 2 nines, using Rydberg mediated interaction to create gates between 2 ground states, like 2 hyperfine ground states. So this is starting to become, really exciting and high enough fidelity to do quite incredible things, especially at scale with hundreds of atoms. And in the context of networking, this whole platform can also be integrated with optical cavities, for example, and people are thinking about this, including myself, to take this technology and sort of bring it beyond just one experiment, one lab, and sort of distribute it over long distances in principle. Okay, so coming back to the kind of the main narrative here, I want to focus on measurements, and the claim is that this is the one thing we're actually not very good at, and the one thing that I think a lot of work needs to be done. It's something I'm quite excited about. So how does measurement work? Well, in neutral atoms that also trapped ions, all measurement is sort of mapped onto the atom either being bright or dark. That's really all it is. And so here's a picture of a one-dimensional array, and you know where your tweezers are, so you know where atoms should be. And then if you look at some region of interest, some site, you can count the photons within that region, and you can create a histogram of whether there's 0 atoms or 1 atom. And how well you could do this? Well, this is just limited by how bright your atom can be, or for how long your atom can scatter light. And if that's not limited by any kind of atomic physics, then it should only be limited by how good your vacuum quality is in the chamber. And so the record, to my knowledge, with a vacuum limited lifetime of several minutes, is about 4 nines in fidelity and like 3 nines in survival. And you get a histogram like this where there's really kind of nothing in between. Okay, so that doesn't look like measurement is a problem. That looks really good, right? So what's the problem? Well, so this is just detecting whether you have an atom or not. This is not asking the question, what state was your qubit in? And this is actually kind of slow. So single qubit, 2 qubit gates are on the kind of microsecond time scale. So you would want measurement to be kind of on a similar time scale in principle. So this is extremely long. Yeah. Excellent question. Yes, in principle, yes. Okay, but the other general problem here is these measurements are global, meaning we're measuring all of these qubits at the same time. And I'll comment on that in a minute. But how is atom readout not the same as qubit readout? Well, the problem is you have, with atoms with complicated structure, many states, you have like limited cyclicity, meaning that the state that you want to be bright is not perfectly bright to good enough precision, and your dark state similarly is not dark long enough to good enough precision. So here, to create a histogram like this, you would want to collect, say, tens of photons, maybe 50. Your collection efficiency is low. Assume you need to scatter hundreds, maybe 1,000 photons. You have all this complex level structure. There's pathways to scatter to the wrong state and for your bright state to become dark and your dark state to become bright. So typically, in fact, what people do is they actually just they kill one of their 2 qubit states. So if the atom was in that state, they actually physically remove it from the trap, and then they convert this readout back just to detection. Is there an atom or not? Okay? So if you want to avoid that, probably you have to really embrace the atomic physics and figure out how to use this level structure or clean it up. And a little bit has been done there, including things that I did with a different class of atomic species, which I'll mention in a minute. And then some of it recently was sort of brute force using perfect polarization, blah, blah, blah. And I'll comment on this a bit more detail later on, where we started to kind of go in this direction and have some pretty exciting results, I'd say. But also I want to comment on this global part, because this is very important. So for a lot of the things I showed, you'd want to be able to, at will, go in and measure single qubits wherever you want. So here's an example of a random circuit where you're just putting in single qubit measurements. But that's actually also really hard, generally. And with neutral atoms, not much has been demonstrated in that direction. And part of the reason is you'd want to probe, you need to scatter hundreds of photons off of one atom without that affecting any neighboring atom. So if you have some dense array, in principle, you could imagine sending a beam onto only one atom. However, you need to keep it cold because you're scattering so many photons, it has to not boil out of your trap in 3D, which means typically that you require beams from several directions. But even if you could do that, the photons that that atom is scattering could go and hit all the other atoms around in a pretty densely packed array. So in the AMO context, we have a few solutions there, and mostly we're kind of inspired by trapped ions. And so one approach is sort of zoning. You can take your qubits you want to measure, physically move them kind of far away where you're not worried about things being close to each other. And people have done this sort of coherent transport now in atom arrays, which is pretty exciting. You could use two species where they just have different wavelengths and they're just decoupled enough that you can like entangle them with Rydberg and then perform measurements of just one species without the other being affected. And what I'm going to come to a bit more now is use a technique called shelving, where you really embrace atomic physics and you find a level structure that allows you to kind of hide your quantum information in states that are decoupled from the states you want to use for measurement and readout. Cooling and readout.
Yes, I would have assumed. Tweezer or something that with some big.
Yeah, good question. Like local light shifts. So people have done this a little bit. In fact, people have done it recently with strontium, where you have transitions that are relatively narrow. I think the problem is with alkalis or with most systems, the line width of the transition that you're using is about megahertz or so. And getting a light shift, you know, if you really want crosstalk suppressed by 2 nines or whatever, you'd probably want hundreds of megahertz light shift, which is pretty hard to do. So either you use a pretty narrow line, which slows everything down, or that's a bit challenging. Now, people have done this like in an optical cavity where your collection efficiency is much higher and you need much fewer photons. And that seems like that could perhaps work a bit better. Okay, so what I want to tell you now is kind of give you a brief overview of our sort of vision here and how we can sort of embrace this issue with measurement, really kind of make it fast, non-destructive, be able to do it mid-circuit, and crucially combine this with the toolbox that already exists for single qubit, 2 qubit gates in a scalable way. Okay, so to do that, I'm going to talk a little bit about atomic physics. I haven't made much distinction between alkalis or alkaline earths. Here we're going to embrace the second group of the periodic table. In fact, ytterbium is not in the second group of the periodic table, as many of you know, but it's kind of an imposter because its F shell is full, so its outer shell just looks like 2 electrons. And in fact, only one of these alkaline earths is strontium. It's kind of the only one that's actually useful. But they all have this level structure, alkaline earth-like level structure. And they're sort of helium-like, so they're broken into spin singlet states and spin triplet states. And on the triplet side, the lowest energy states are these group of p states here. And they're dipole forbidden to decay by the triplet to singlet electric dipole selection rule. And this quantum number J is the total electron angular momentum. And so there's another selection rule saying you can't go from J equals 0 to J equals 0. So that one is in fact doubly forbidden. So what that means is you get some pretty narrow transitions here. And why are they not just like 0 line width? Well, because you get sort of spin orbit coupling and hyperfine mixing that very weakly mix between singlet and triplet. But you're still essentially in this basis. It's still a good basis. You just get sort of very weak coupling between these two states. And in fact, this lowest energy state, this is a so-called optical clock transition where people perform timekeeping now at sort of 10 to the minus 19 level of precision. Because you have a transition here that's like millihertz line width, and it's an optical transition with frequency of hundreds of terahertz. So that's an extremely high quality factor. Okay, and so what we did with strontium I was a postdoc, this is quite successful already, is you can go to this metastable state. It has a very long lifetime because of this weak decay. You can think of it as essentially a new ground state on the time scale of any of your experiment you want to do. And then you can go to these highly excited Rydberg states from this metastable state. And that has the advantage that this transition is already fairly strong because there's better sort of radio wave function overlap. And it's a single photon excitation to an S-series Rydberg states. And S-series Rydberg states are quite nice compared to D, where they're more sensitive to electric fields and they're more anisotropic, for example. Yeah. Sorry, say. How do we get in? Yeah, excellent question. So I'll talk about this a little bit later. But it turns out if there's any line width here, if you get a big or sort of medium-sized laser, you can actually you can power broaden this and actually get it to go pretty fast. So it's not too bad actually. This has been explored now just for a handful of years. So it's kind of a new direction to have these alkaline earths in this single atom control, this tweezer array sort of context. And there's a few groups kind of leading this direction, including my former advisor. And to go from here, what we want to do is now to think about how adding nuclear spin, going to an isotope that has a nice, convenient nuclear spin of 1/2, what does that do to this level structure? What else does this give us? So in these states where the total electron angular momentum is 0, you get a pure, just nuclear spin qubit. So you have I equals 1/2, but J equals 0. And so the splitting is small, but it's sort of a nice protected degree of freedom that you sort of have 2 copies of in your atom. And remember, this state lives for a very, very long time. And so people are already starting to explore this and have long coherence time. And just a bit of a spoiler, I think we kind of do too now, as I'll show you in a minute. And you can actually control them with high fidelity and can read them out pretty well, which I'll also mention. And in fact, people have already used them to do Rydberg-based entanglement. Okay? So maybe an extension of that is you can take the advantage of the fact that you have 2 pairs of qubits, if you like. It's almost 2 qubits with one atom, within one atom. And in trapped ions and in neutral atoms, we're thinking about sort of this so-called OMG architecture where you can make full advantage of a ground qubit, a metastable qubit, or even an optical qubit, or some combination thereof. Okay? So, in the context of measurement, how would this help with this mid-circuit measurement problem? Well, what you can do is you can use your metastable qubit, this would be your computational basis, and then your probing, your cooling, everything else is from this ground state down here. And so if you send in a laser on the transition from the ground state to some other state, that doesn't couple at all to this metastable state. So it's sort of shelved up there. It's just protected and immune to that measurement. And that means you can perform like global pulses. You can have beams from all directions. You don't have to worry about selectivity. You just need selectivity to perform what I would call kind of a read-enable operation that selectively transfers the qubit you want to measure down to the state that's on which you perform that sort of measurement. And so an example of kind of the minimal level structure in a random circuit that you would make in this way, this would be your computational qubit here. You have these Rydberg mediated entanglement from this upper state, and then you can controllably at the single qubit level go down to this kind of readout state that you would probe with this transition there. Okay? So, and another nice feature, I'm not going to focus on this in this talk, but again with this same metastable state, this long-lived state in this ytterbium-171 isotope we use, there are strong transitions in a suitable wavelength range to use for quantum networking. So we want to also bring that aspect here, where we can extend this entire toolbox to also include the ability to perform remote entanglement. So that's something we're also working towards. Okay, so before we actually get into what we're doing, I want to just very quickly kind of advertise, not really fully explain. When you use an optical transition, you have to be careful to be aware that the K vector, the momentum associated with that light, can sort of couple to the motion of your atom. So we've studied this in quite some detail, and other groups have. The takeaway message is that you want your Rabi frequency, how fast you drive that clock transition to be fast, particularly compared to your motional timescales in the trap. But if you're fairly cold, 5 to 10 microkelvin, and you can drive that pretty fast, things actually work pretty well. It looks pretty promising. So even more technical, and again, I'm sort of just advertising things here. The problem is, with driving optical transitions at frequencies of a couple hundred kilohertz is you have to be very aware of noise on your laser at that frequency. So there are some techniques to remove that kind of noise, but they're not particularly well suited for such a narrow line width laser to drive a clock transition. And particularly if it's a complicated, maybe even commercial laser, you would kind of not be able to use standard techniques. So we sort of invented a new technique where you use a small amount of transmitted light through a cavity to gain real-time information about phase fluctuations that you can then correct with an active optical device. Okay, so what I'd like to talk about now towards the end is what we're doing on our experiments. And before getting into much detail there, so I'm not too rushed at the end, I want to acknowledge the people that actually do the work. So we have a fairly large and very strong group already, and many of them are in the audience. And after the first year or so, I haven't really done much myself. So it's really all these guys that are doing everything that I'm about to show you. So we have two ytterbium atom array experiments. I'm mostly going to talk about the first one. I will say a word or two about the second, where we want to have an atom array in an optical cavity, and several groups are now moving in this direction. The cavity can enhance your atom-photon coupling, which can allow you to perform measurements much, much faster. And you can also sort of vary the strength of the measurement from strong to weak, whereas in sort of the normal context of measurement with atom arrays, it's always strong, fully projective measurements. And stronger atom-photon coupling, of course, is good for networking and distributed computing, where you use the photons to create remote entanglement. And then also this idea that I mentioned of spin squeezing to create sort of a collective measurements that project the system into an entangled state. Here we can do that, and the spin squeezing is particularly relevant since we have these optical atomic clock transitions, which would actually benefit from this kind of squeezing. Okay, so now focusing on the first experiment, we're using atom arrays in tweezers of a certain wavelength, specific wavelength. I'll mention in a minute what that means. So far, we're working with, or we have worked with, kind of small arrays of atoms in a kind of a standard trap depth, and we image and cool on this one of these forbidden states, the broader of the two, so it's narrow but not too narrow. And the atoms are pretty cold so far, particularly in the radial direction. And this is what kind of a typical histogram looks like, where we get, on average, maybe about 70% of the time, we load one atom versus 0, and we can differentiate the two pretty well. This is like a release and recapture measurement that where we turn off the tweezer and then wait some time and turn it back on. That gives us a flavor of the temperature of our atoms. One sort of limitation that's a bit intrinsic to the species so far is there's tweezer-induced like Raman scatter to other states. That in principle, this hole could be plugged, but for us at the moment, this limits our survival under this type of image to about 0.96 or so. So that's something we have to kind of live with for now, but it's not prohibitive at this point. So a word about the tweezer wavelength that we choose. So this clock magic, that means it's the same polarizability for both the ground state and this very long-lived metastable state. So the two states feel the same tweezer. And then this 3p1, these are the states we use for imaging and cooling. You can see that the polarizability is a bit different for those, the different MJs of those two states. But this is for isotopes with 0 nuclear spin. And what the nuclear spin actually does is it mixes these two different MJ states from hyperfine interaction. You can see one is higher than the desired polarizability, one is lower. It mixes those two and actually sort of puts it right exactly where we want and gives us kind of a triply magic condition where that state, that particular MF of the isotope we use is also magic with the other two states. And the other state is actually kind of close by as well. We can resolve all 4 of the different MFs of that state. So this is kind of a Zeeman map versus magnetic field of where those 4 states are. And since the transition is relatively narrow, we can resolve all of them. And so that kind of brings me now to the point and back to this question of measurement. Can we do non-destructive qubit readout this way? How would qubit readout actually work? So the type of measurement I just showed, we measure on a transition here of these different MFs in this excited state that intentionally couples to both of the ground states such that they both stay bright. And this transition is relatively narrow, about 100 or 200 kilohertz, and the splitting up here is split by electron G factors, so it's megahertz per Gauss. So by applying some field, these states become further and further apart. We choose to use this -1/2 state here. But what if we choose instead to go stretched on this state over here, where by polarization selection rules, you can decay only to 0, and 0 is the only one that can go up to there. Then as you apply a B field and these states are moving further and further apart, in principle, this then becomes state selective. Okay, so only one state is bright and the other is dark. And there's a little bit of polarizability difference here, but it turns out it goes in a favorable way, meaning the upper state is a little bit deeper trapped than the ground state. And this actually seems to work quite well, and we utilized this sort of regime for strontium previously. So then, is that a question? In the histogram? Yeah, so you can image longer and longer, and then your bright atom gets brighter and brighter. The problem is there's a small probability that something bad can happen when you're scattering photons and you actually lose your atom. In our case, you can have some Raman off-resonance scattering to some dark state. And so the goal is you basically want to use the shortest time possible such that they're sufficiently separated. So there's kind of a trade-off. Okay, so we don't need any polarization control to do this. We just need energy selection to actually separate these states well enough. And if you think about how high in field you need to go, this is a plot of optical block equations, like rate equations versus magnetic field. This is sort of the rate of like going to the wrong state when you do a typical image on one of your states. And it looks like already a few tens of Gauss, maybe 50, 60 Gauss, that seems high enough to really fully isolate that transition such that one of your qubit states is bright and the other is dark. So we've been playing around with this. At the moment, we're at this field here, like 18.5, which is not quite as high as we would want to be, and we'll push higher later on. But what we're seeing already is, I think, pretty promising here. So on this stretched imaging, the image performance is pretty similar. We can get pretty nice histograms for the separation of the two states. The temperature during imaging is similar, not so different than the other imaging. And the survival, it's already too preliminary for me to really say probably, but it's in principle kind of close to what we expect based on this off-resonance sort of loss mechanism that I mentioned. And so then we can ask the question, so is this now qubit readout? Is this state resolved? And so we can control the state. We add in Rabi oscillations on the ground state by driving an AC magnetic field perpendicular to our DC magnetic field. And we run a circuit like this, where we initialize in 0, we perform a measurement, then we do some Rabi oscillation, rotate some angle that depends on time, and then measure again. Now, one thing to point out already is there's no optical pumping, there's no cooling, there's no like shelving or de-shelving kind of tucked in here after the imaging. There's really nothing in between. And one other thing to mention is we know that there's some fraction of atom loss. We also know that since we're not quite at high enough field, there's going to be a little bit of transfer from the state that's supposed to be bright to the state that's supposed to be dark. But this is what we're seeing for Rabi oscillations. And the coherence time, it seems to be kind of on the order of a second or so, which is perhaps about what we might expect. And again, there are reasons why this contrast is kind of limited, and this is very preliminary. So to now really explore the state resolved readout part, you can start with a random state initially and do a similar experiment. And again, so here probably we would ultimately need a third image because there are 3 pieces of information. The 2 qubit states and whether you actually have an atom at all. So this is just stochastic loading. So in some cases, there are not actually atoms there. But what we're seeing now is we see similar Rabi oscillations, and this is sort of grouped, this data, by the outcome of this first measurement. So if you measure 0, then your Rabi oscillation starts from 0. If you measure 1, then your Rabi oscillation sort of starts from 1. And the contrast is pretty similar to what we saw here, pretty good. And again, we really need a third image to classify cases where there are atom loss. Okay, so why do I call this quantum non-demolition? So someone asked already, so what do I mean by that? Well, really that's kind of like textbook readout. So when you perform a measurement, you measure that you're in 0, then that's what you're in afterwards. And same with 1. You should not need to do optical pumping, cooling, shelving, deshelving, any of that kind of stuff. And of course, if you have actual atom loss, which as I mentioned, most imaging cases actually have, certainly that's not quantum non-demolition. So this is preliminary, but I think that's what really kind of what we're seeing here now. I think it's working pretty nicely. And this might already be applicable for like measurement-based computing, where you start with something like a cluster state, and then you just perform a series of measurements like this, and you always stay in that basis, and you just kind of measure under different axes. There are other things where you imagine you use like an O-type, like an optical clock transition qubit. In principle, you could transfer from the bright state, or from the dark state to the bright state to measure some subset of your clock qubit atoms, like during a computation. And then also actually this ability is pretty similar to how you would do distributed computing or remote entanglement generation. There again, you'd want to use the same sort of ground nuclear spin qubit. Yeah. The two qubits that we're talking about here. This is just the ground nuclear spin. So this is still in the ground state. It's just the nuclear spin degree of freedom. We're just performing a measurement on, go back one second. We're performing a measurement on a transition here from using some other excited state, but we need to be able to control kind of which of these states up here are involved. But the qubit I was talking about is just this nuclear spin qubit down here. Yeah, that long-lived triplet state, we'll come to that later on. We're sort of just building towards that now. Yeah. Uh-huh. Yeah. So just to be clear, so this is averaged over hundreds of realizations probably. So on a single shot basis, yeah, you would know what your outcome was, and then you could do whatever you want to do. What I'm showing here. Yeah, in principle, that's what you may want to do, even on a single shot basis. You know your measurement outcome, and then you use that in real time to adjust something depending on what you're trying to do. But the requirements are still the same, the ability is still the same, and that's what we're showing here in just an averaged over and over, and the two groupings are just based on the outcome of this first readout. Okay, so it's taking me kind of towards the end here, running a bit out of time. Just very quickly, the second experiment is also making kind of nice progress now. So the atom array in the cavity is a bit complicated, and we're towards the end of the design phase. Almost everything has been ordered, and we're kind of preparing to start building the science chamber, the 3D MOT region. But the source region, the 2D MOT region, is built and is functioning already. So we have ytterbium fluorescence here, and recently a two-dimensional magneto-optical trap in this new system. Okay, so that brings me to the end. Just a very quick summary in our progress towards controlling openness and adding it as kind of a new circuit element, if you like, in our Rydberg atom array platform. And I'll just kind of leave you with, again, a picture of all the people that are doing this excellent work in the lab. And I'll thank you for your attention. Yeah.
So at the very beginning of the talk, you essentially do wash out.
Yes, yes.
How
Here-
can you measure some local box?
Yes, these are excellent questions. So part of the question is so-called like sampling or sort of measurement sampling question, where you every time you run the experiment, you have different measurement outcomes in all of these measurements, and you would want to kind of post-select on a certain trajectory. But then it's sort of exponentially unfavorable in taking data because it's very unlikely that you get that outcome if you have a large system. So this is a known problem. There's some, people are thinking about this, there may be some shortcuts. There's also related aspects of this phase diagram where you can, again, add real-time like feed forward and actually use those measurement outcomes to sort of change things in your circuit. And then there's so-called like steering transitions, phase transitions. Like they're both area law, like it's maybe hard to go between area law and volume law, but there is a phase diagram in this kind of circuit too if you add in feedback to be able to sort of steer your system, which is again a little bit related to like many-body teleportation, for example. The other part of the question is, what do you actually measure? So a lot of people talk about like measuring entanglement entropy, which of course is hard. But there are shortcuts. You can have like witness qubits and do clever tricks with certain ancilla qubits to try to measure these sort of things. But I think there's also open questions in how well you could sort of characterize these type of phase transitions. Tool and yes, I think that's a tool that people use as well. Yeah. Okay. Any other questions? Okay, well, I guess I'm also the host. So thank you for your attention. Please attend the next several talks. And yeah, we'll see you next week.